of ISNT and life member of ASNT, MSI, AMSI, INSIS. He is the editorial board of ISNT's Journal of NDE. That is, regularly we are releasing in ISNT journal, and is a reviewer of several other international journals. He has written many co-author for advanced NDE books. Actually, it is there. You can, during your free time, you can get that links. I welcome Dr. Shyam to the stage, please.
While we wait for the slide to come up, again, I'll add my warm words of welcome to all of you who have taken time on a Saturday to come here and spend time at the Pallakki NDT Excellence Center to learn a little bit about advanced NDE. As Shashidhar mentioned, this is just to give you an exposure of what is happening in the world of advanced NDE to a combination of both a little bit of theory, which you'll see now, and a lot of practicals, demonstrations, which will actually show you how these advanced entities work, which I believe is very important. All of you to take back to your respective industries and put it into practice. So, as Shashidhar mentioned, I think my talk, we're going to focus on why do we need advanced entity, A, and B, just give you a very high-level glimpse of all the things which are going around in the world, many of which you are aware of, many which may be new to you, and the important thing is to absorb and see what is good for your industry and adopt it accordingly. So that's the thing. We'll go to. Okay. So I obviously, most of the time I start my talk with giving a tribute to my mentor and guru, Dr. Baldev Raj, who many of you are familiar, was the doyen of NDT for India. And I worked with him at Indira Gandhi Center for Atomic Research. He was the one who brought me into the field of NDT. And right from 1984, when the world was still looking only at conventional NDT, he was the one who introduced many of us, my colleague Manoharan, who is also going to speak. We both are kind of brought up under the guidance and mentorship of Dr. Baldev Raj. So I obviously want to pay tribute to him that whatever I am today, I owe almost a lot of it to him. So NDE is a cradle-to-grave technology, which means it starts right from the raw materials and goes on till the end of life. You manufacture a product, you do NDE, you put it into service, you do in-service inspection, you do residual life assessment, and then right till the end of life. That's why it's a cradle-to-grave, which means when metal or material is born in the mines to the time you scrap the entire component and discard and say it cannot be used, we use it. So that is cradle to grave. So I do have much more charts than what I can cover. So I will be skipping some of them or maybe going very fast, but hopefully we'll be able to convey the message. So the way NDE has developed is that we used to be very reactive, which means we find something, then we act. And then we became proactive, which means trying to predict or at least say, can be prevented. And today it's almost entirely predictive. And why advanced NDT? Because just living with conventional NDT, we can probably be a little reactive or proactive. But to be predictive, you need to adopt all the recent technologies to be able to cater to the industrial world. And there are lots of details which I will not go into, but basically the advanced NDT came because there was a need from the industry. And as human beings, we all know we are always eager to do something better and better. If something is happening at some pace, we are able to inspect a component, one component for say 5 minutes. We are not happy. We want to improve productivity. We try to make it 2.5 minutes, then go to 1 minute. So, but when that happens, you need better and better technologies to assist you to make that happen. Similarly, the demands of industries in terms of doing things faster, finding smaller defects, complex designs, newer materials, everything gives rise to advanced NDT. There are hundreds of NDT methods, obviously. Some become more popular because industry finds it very useful. Some take more time to establish. And that's a natural phenomenon. We don't have to worry about it. But as you learn more and adopt it, that is when we will see more and more being developed. And the reason for a lot of the advanced NDE is also that we are dealing with a diverse things. Unlike NDT is always compared to the medical doctors in some sense because they also do something similar. But the difference between a medical doctor trying to always inspect a human being, which is typically very, little difference in size and shape. Materials are almost very similar. Okay, but when in the industry you're dealing with all kinds of materials, shapes, sizes, complexities. Okay, and then, during factory in the manufacture, you are able to do it, but when you go out and install it, the same thing, like a heat exchanger tube, right? The heat exchanger tube, when manufactured at BHEL, for example, you have access to all sides of the tube in ID, OD, everything, and you can do different types of inspection. The moment it is installed as a heat exchanger in a plant, you are very limited. You have only access to ID of the tube. So you can't really, do many things which you were able to do in the factory. So that leads to, again, advanced NDT. Yeah, okay. So this is just an example of how, aerospace industry, constantly developing because, people want to fly faster. What used to take probably, 30, 40 hours to reach from, say, India to the US, changing at multiple locations in between. Today, you have a direct flight from Bangalore to San Francisco, which flies in 15 hours. Okay. Why did that happen? It was because of the constant development which happened, say, in the engine's capacity. Okay. The other demand is that, we want to have less pollution. We want to have, faster speeds. You want to have less noise. All these are demands as people fly more and more. And then, people like those who manufacture aircraft engines, for example, because I was in GE, I quote this example, we try to make engines lighter and lighter, more efficient and so on. So we came up with something called the carbon fiber composite blade with a titanium edge for the GE90 engine. Very, very, looks simple, extremely complex to manufacture and still more complex to inspect. But because we were able to manufacture and inspect with all the advanced NDT, including CT, computed tomography and many things, today you are flying, on the GE90 engine, both within India and outside India. And that was possible because of all the developments in manufacturing, all the developments in materials, and all the developments in inspection. If these three do not happen together, if you can manufacture but you cannot inspect, nobody, the DGC or FAA will not give you permission to fly. So that's the challenge. Similarly, when you go to wind turbines, extremely big structures, long structures made of fiber, glass fiber composites, very tough to inspect. And so while they were busy manufacturing with newer materials, the NDE and the inspection community was trying to see how to inspect them better and better. So this is typically how your wish list will look like. I want better productivity, I want high product quality, etc. Repeatable decisions, everything is there. So you have to cater to all this, you need again advanced NDT. So advances in NDE can be of different types. You had already conventional NDT and you built on that. Just as an example, you had, and we'll talk about that, so I won't cover that now. And then in the same modality, and then there are newer techniques. We discovered physical principles which can be very used. For example, infrared thermography, okay, which wasn't existing even 30 years ago. And then suddenly we found that just by using IR imaging, we can actually figure out a lot of things like defects, etc. And then there is a lot of other developments, automation and things like that, which we'll talk about a little bit. So these are the challenges which any industry faces. You want higher productivity, you want best in product quality, you want minimum rejects, you want no forced outages. A thermal power plant, a nuclear power plant, a refinery, or even the aircraft, take Indigo or Air India or whatever. They not want the aircraft to be standing on the ground for greater than 8 hours, because that's like the minimum when you come back at midnight and fly next day morning. They want it to be minimum, so which means there should be no issue on the airframe as well as in the engine. So you need all the advanced techniques again to do that. You need a lot of things like, as we go to advanced techniques, we have more data volumes, how to handle that and things like that. And characteristics, you saw the picture on the various industries. So we are dealing with tall structures, We are dealing with large area structures, surface area. We are dealing with large lengths like the wind turbine blade. Remote locations. Now we have wind turbines right in the middle of the sea. How do you take care of that? How do you inspect that frequently and take care of that? Everybody wants minimum shutdown period. If 10 years ago, industry were okay with a 15-day shutdown, typically during, say, December or any time when the load is less. Today, they want to bring it down to 3 days or 4 days. How can I just have shutdown of 3-4 days, but still do a good job of inspection? And that cannot be done unless advanced NDT is there. Inaccessible areas, design becomes complex. Many areas are inaccessible. So how do I do? So design for inspectability and so on. So a lot of things. So I'm not going to get into the details for that. So yeah, a lot of things. But so this is a classic thing. We always see that, technology is out in the market, but its adoption always takes time. And that is because this is the typical, what is called as the, growth curve. There will always be, initial interest, then sometimes the interest will die. And then suddenly you find some things happen around you, due to which you see the peak of inflated expectation. Then again it falls, and then it steadies. So look at NDT, look at any of the advanced NDT techniques, be it phased array, be it digital radiography, be it some of the advanced eddy current. You'll see a pattern. This is how technology adoption happens. And so we need to be patient. We need to continue to do what we have to do. And eventually you will see that some techniques which the industry finds useful will go into what is called as the plateau of productivity. So that is where we really need to bring most of the techniques. Some will take more time, some will take less time. So just quickly covering a few advances which have happened. FPI, which is kind of considered a conventional technique. How does it become advanced? When you bring in automation. Today, the entire inspection can be automated. The interpretation of the FPI signals can be automated using artificial intelligence. X-ray methods I won't touch because we are going to have two experts talking about it, CR, DR, everything, so I won't talk about it. Ultrasound again will be talked about, I won't touch upon it, but all I want to say is that how did the new techniques come? Because there was a demand from industry. You were using a single ultrasound probe and trying to do inspection. It was taking time, you were unable to do everything you wanted. That's when industry said, can we have something? And the good or bad thing about all these advanced techniques, we have adopted it from healthcare industry. Phased array ultrasound was being used by doctors several decades ago. But then slowly in the industrial world, we also translated and tried to make it useful. So this is just a glance of, you have guided wave ultrasound, you have phased array, you have EMATs, okay, you have nonlinear ultrasound. Just in ultrasound, I can list about 10 different techniques. Each one has a unique advantage, a unique benefit, and that is the reason why you see all of them in the market, and you have to use what is useful. Because when we wanted to inspect long lengths of pipes, guided wave ultrasound came into picture. So EMAT, when you wanted to do high temperature inspections, EMAT, because it is non-contact, kind of helped us, and so on and so forth. Similarly, in electromagnetic or eddy current ND, the earliest was the most conventional ND, which was doing some parts of the job. Then we realized I want to, for example, in a heat exchanger, when we have support plate or baffle plates, if there was a defect under the support plate or baffle plate, we were unable to detect with a single frequency, and then came multi-frequency. Then we realized that we can do very good job if it was just electrically conductive, like copper, brass, stainless steel and all. But what about carbon steel? Conventional eddy current could not do a good job of carbon steel heat exchanger inspection. That is when we got techniques like remote field eddy current, low frequency, full saturation, etc. Then we also found that to cover large area, it was very difficult. Then we got eddy current array. And today arrays are becoming very popular. You can do very fast inspection because it has several sensors and so on. Pulsed eddy current. Again, because we found that we could not penetrate much depth with the conventional eddy current because of skin effect. And then came pulsed eddy current, which is capable of penetrating through insulation. So problems like corrosion under insulation and many other things today can be solved with pulsed eddy. So all these advances took place because there was a limitation in the conventional method. So most of it was industry demand plus limitations of conventional method. When you put together, came advanced NDT. Some became popular, some took time. So there are several things which I will not cover. There is microwave NDE, which today is available for non-metallic materials. So composites, plastics, FRPs, HDPs, everything today you can do microwave NDE, and it's all available within the country. We also have terahertz NDE, which again goes to still higher frequencies, excellent for coatings and for composite and any non-metallic materials. And then, of course, you all have heard about acoustic emission when you want to inspect a large vessel, and monitor it, not inspect, rather monitor it, you use acoustic emission. And then infrared imaging I was talking about. So, you can really do wonders with IR imaging. Non-contact, large area, quickly screening you can do and find out lots of defects. Again, applicable to electrical installations, composite materials, and many, many applications. And magnetic techniques, again, you are familiar with magnetic particle inspection, but just looking at the characteristics of the BH curve, you can do many, many things, okay? Plus, there is a phenomenon called Barkhausen noise, which is very unique to the microstructure of the material. So magnetic methods, again, very powerful, gear inspection, grinding burns, many things. So again, commercial equipment. So these are all advanced NDE which grew from fundamental magnetic particle inspection. Modeling and simulation is again a very powerful tool. So you can do today with the tools available, fantastic job of not having to do a real experiment. You can design sensors, you can do probability of detection, reliability studies. I mean, the thing is so powerful that you can do everything sitting on the computer first, assess what is best, and then take it up. So, which is also an advanced form of NDE. Automation is the next big thing, so I'll probably spend just a few minutes, and that is what was referred to as NDE 4.0. So slowly, everybody wants to automate everything, not just the inspection process, not just the analysis of the signals, but even the decision making. Okay, you'll hear many things about things like ADR, automated defect recognition, and so on. So everybody has heard the term Industry 4.0. So this is how the revolutions have happened. Earlier it was the steam engine, and then came the electrical powered things in Industry 2.0. Then came a little bit of computers in 3.0. And today we are talking about integrating physical and digital, which is cyber physical, and that is called Industry 4.0. So this is a topic by itself, and we won't spend too much time on that. So even in the industry, NDE world, that is how it happened. It started with the most simple thing, just NDE 0.0, human senses, just by hearing sound and other things, visual inspection was NDE 0.0. Then we went to 1.0, we were with dye-penetrant testing, we were able to see the surface. In 2.0, we started going deeper inside with ultrasound and other things. Then 3.0, we started doing digital processing, okay? Everything became a little more digital. And with NDE 4.0, which is what we are now going towards, we want to be predictive and have a foresight of everything which is happening. So I will skip some of this. So the heart of NDE 4.0 is digitization, digitalization, and digital transformation. Okay, and a lot of it you will hear, especially in both the X-ray and phased array thing, how digitalization is taking place. And every sector, irrespective of the industry, is trying to adopt it slowly and steadily. So these are the pillars of what we call as NDE 4.0. So on one hand, you have the techniques, ultrasound, eddy current, and everything, technologies. But when you combine with powerful things like artificial intelligence, augmented virtual realities, robotics, drones, Internet of Things, when you combine this, you have such a powerful platform by which you can do miracles which were not possible even 8 to 10 years ago. So I won't be going into any of this, but AI obviously is the big thing which can be used. You hear it everywhere. It's happening to you every day in your mobile phones and every places. Why can't we utilize that in a better way to make decisions, to speed up things, to reduce human fatigue? Many things are there. And there is always this question about whether AI will replace human being. The answer is no. Okay, you need human beings to create AI, so you will never go away. So lots of examples of how we are doing, won't get into the details. So this is how AI can help in phased array ultrasound image interpretation, which is, as we all know, a little tough. Okay, it's not as easy as conventional UT. So you can use AI for that. You can use AI for FPI analysis, okay, automated. The FPI image can be taken and automatically analyzed. You can, they are using it for wind turbine manufacture by integrating it with design and so on and so forth. ADR, which will be talked about a little later. So how do you do automated or assisted defect recognition? Today, if you are seeing 500 images in one shift, just as an example, with the help of AI, you can ask the algorithm to do the screening first and bring down the 500 to maybe 100. And that way you are actually becoming more efficient because you're taking only the 100 critical images and analyzing. The remaining 400 has nothing of importance. So the human being can concentrate on the 100 critical images rather than all the 500 images, just as an example. This is the ADR part which I was telling, from the digital image, how to do it and all that. The other thing is, of course, robotics. With robotics, again, you can do wonders. Again, none of this is actually going to replace human beings because you need still people to do everything. But it can make your process very efficient. So here is an example of how the robot is doing a tank scan. And you can, the display, how you display it gives somebody an immediate information that here are my critical. So if you want to do a better, finer inspection, you can just go to the red areas and do. The green areas are good. No need to waste your time there. But earlier, or typically what we do is we try to spend on the entire tank. So this can become very, very efficient, including large structures like boilers. Okay, you put a scaffolding, then a person will climb up there, as you can see. Then he has to do the cleaning. Then he has to do, ultrasonic thickness measurement. And with that the other robot which is there on top, or this one, as you can see, you can do visual. You can even do ultrasound thickness measurements. X-ray, again, is using a lot of robotics. Power plant boiler, which is what I was talking of. Huge structures, lots of tubes, and measurement is a challenge. So this is probably, you can see, you are using rope techniques or scaffolding to do it. All that could be potentially eliminated by using robotics. Okay, so some more robotics, I won't get into that. Let's see. Can you click on that? This is a video, hopefully it runs. On the screen. Yeah. Okay. Maybe the volume won't play, but this is an example of Rolls-Royce developing a bug robot. It can actually go inside the aircraft engine. Aircraft engine is so compact. You have so many, turbine blades and compressor blades and all. So you can actually let down, and if you believe this is fantasy or science fiction, no, it is not. It is actually existing. So those all, unfortunately, the volume is not there. So, but basically he's taking. So, when you have very close packed structures like aircraft engines, a human being obviously cannot go unless you open it up. You don't want to open it up. So that's when these kind of what is called as robots, which are miniaturized bugs, which can actually go in and do that. I think they'll, you can see that, how it goes inside. Very complex. Go to the actual location. It can actually do the inspection, and it can also do a repair. Okay? If the coating has gone, it can do some kind of a coating there. And post repair, you do again an inspection. And then it comes out. And then you're done with the inspection. So typically airlines do not want thing to be on the ground longer. These are kind of the tools. And as I mentioned, this is not science fiction. Of course, you're not still available commercially, many of these, but still it's just not a matter of few years when you'll probably see all of that. So here it has finished its job and going back, okay, and each one of them is a robot by itself, and that's the size. It's in the size, it's holding on your palm. That's your size of that robot, okay? So that's the kind of advancement where robotics combined with inspection, we can actually do a lot of wonders. I know I am almost out of time, so I'll quickly, we'll skip that. So that's how it will be. It will be a combination of robots, drones, inspection tools, trying to do all kinds of inspection, which will give you a total information on the thing. So that's the scenario of the future. Okay, you will have AR glasses, the inspector can see through it and so on and so forth. The other big thing, last point which I'll quickly make is about drones. You're hearing about drones everywhere, and drone again is a powerful tool for inspection. We have inspection sensors on top of that, we can really do that. So we can do it for wind blades, boilers, all kinds of things. So oil and gas assets, large pipelines, okay, railway assets, you know, you can actually measure the gauge distance between the railway tracks using the drone and some of the visual sensors. Go inside a tunnel, which is very difficult to typically inspect. Lots of things in the power industry, solar farm, yeah, you can inspect an entire solar farm, okay. Of course, wind turbines, because every time somebody has to climb up, not easy. Yeah, this is how people do it today. We can replace that with a visual high definition camera as well as IR camera to do drone-based inspections. And typically in 40 minutes, what would have taken 2 days or 3 days, today you can do 3 blades in 40 minutes. Okay, you can do the external, before an aircraft delivery happens, they do an entire drone-based inspection to see there are no scratches, no dents, everything and so on. And if you take the drone-based images, apply AI on that, you can automatically detect. So you can see here corrosion areas in a refinery. Automatically detected from the drone image using AI. And then there is the whole topic of AR, VR, augmented reality and so on, which is so fascinating that it is going to revolutionize the way it is happening. It's going to take a little while to come into the inspection world, but this is how probably in a few years from now, inspection will get done. You'll be getting the entire manual right on your screen. It will guide you what to do next. If you found a defect, what to do, etc., etc. So step-by-step guidance. So that's how the whole, this thing, it will be remote inspections, end-to-end tracking. It can do training of inspection personnel and NDT and so on and so forth. So in summary, advances in ND will continue to happen. Whether you adopt it or not does not matter. It will continue because industry requires it. And sometimes the cost becomes a barrier, but every technique, everything, just like today you're talking about cell phones, how cheap they are, or laptops, how cheap they are. It was very costly, but as it gets used better and better, the cost will come down. And it can be in any part of the inspection ecosystem. It's not just technique. It could be instrumentation. You have seen miniaturized instrumentation, sensor. You have seen wireless sensors, miniaturized sensor, array sensors, okay, software, everything. And combine that with robots, drones, AI, then you have a very powerful system. Advances get usually accepted for regular usage after sufficient validation and availability of standards. So sometimes that is a problem. The technique is there, available in the market. For example, I told you about microwave and terahertz. Microwave and terahertz are available in the market, but unfortunately, except for microwave inspection of HDP butt fusion welds, we do not have any standard. So obviously industry little bit hesitates to adopt it. So it will happen with time. Like CRDR, a decade ago we did not have standards. Now we have for everything, and you can see the adoption is increasing. Every modality has undergone advancements in the last 2 decades, and it will continue to do so. Embrace and adopt advanced NDE in your industry after a careful cost-benefit analysis. It is not that something exists and I have to use it in my industry. You have to decide for your industry whether it makes sense. There is a cost-benefit analysis. Does it give me effective productivity, reliability? What does it do for me as an industry? And of course, we are here as experts available to help you and to do that. And before I formally end, just wanted to share that, we talked a little bit about NDE 4.0. So you are all fortunate that we are going to have this international conference right here in Bangalore at Taj Yeshwantpur, March 3rd to 6th, 2025, okay, where Mr. Shashidhar is the chairman of the organizing committee and I am the convener of this conference. We are expecting about 300 to 350 delegates with at least 100 foreign participants and exhibition. The focus will be on NDE 4.0, all the advancements with respect to how automation is done, how robots can be used, how AI can be used and all. So we do hope most of you or many of you will participate because it's right here in Bangalore. With that, I would like to thank you for your attention And hopefully you got a glimpse of how advanced NDT is growing, why advanced NDT is a necessity. The choice of adoption, slow adoption, fast adoption, etc. is left to the individuals and the individual industries. So thank you very much.
Anybody wants to have some questions? Anyway, we have a question and answer session at the end of this session, evening feedback session. Now, if you have any questions, we'll take questions. Otherwise, I'll go for next talk. Okay. Thank you, Dr. Shyamsunder, for your the wonderful light throwing for advanced NDE, why to adopt NDE. As you see, there is a plenty, it is there, especially for small bots, robots, all these actually. So this is, that is what actually, it never going to stop that advancement. It will be there, and we are to, align to this advancement. With that, I'll thanks Dr. Shyamsunder. As you said, there is a wonderful opportunity for our NDE 4.0. Exclusively, we are talking about advancement in NDE. That is a 4 days fest. It is happening in Bangalore between March 3 to 6, 2025 in Taj Yeshwantpur. The registrations, paper presentations, exhibitions, exhibitors, everything is already started. It is there in the website. So interested candidate can go there. With that, I'll go to this next talk with Mr. T.C. Karthikeyan from Blue Star. So Karthikeyan is worked in past, now presently is in Blue Star, is previously is worked in BHL Trichy and Larsen and Toubro and Plus Veloci in Oman. Is basically is PCN level 2 in ultrasonic testing, especially in advanced technique like paste array, TOFD, and radiography. Is also is holding this BRC level 1. Is working in this almost 14 years in NDT domain, and he has successfully demonstrated many advanced ND equipment. Some major kind like BPCL, HPCL, MRPL, Chevron, Shell, ExxonMobil, and Aramco Saudi. So he has led that significant projects, including LNT, Plus Veloci Oman, and the many such things. Actually, when I asked for his biodata, he has sent about 6 to 8 pages. I said, due to time constraint, I cannot read. Give me a little bit. So with this short, I welcome the young and energetic Mr. Karthikeyan, Blue Star. So over to you, please come.